Okay. Hi, everyone. So good morning, good afternoon, and good evening, depending on where you're joining us from today. On behalf of the NASA Coffees Drive Center and the local organizing committee, I'm very pleased to welcome you all to our one-day virtual workshop titled Solar and Stellar Inertial Modes and Their Implications. We're extremely delighted to see participants from all over the world, spanning many time zones, gathering here to share their work and perspectives. We hope this workshop will spark new conversations and collaborations that continue well beyond today. This workshop will be recorded, so please, I'll send around an email later in the day, so please state if you want your talk to remain recorded or not. Um, today's program consists of 3 sessions, not in this order, due to time zone restrictions, but 1, observations of inertial waves, 2, theoretical and numerical modeling of inertial waves and the role of magnetic fields, and 3, what can inertial waves tell us about solar activity? Each session features 1 or 2 invited talks and several lightning talks, followed by extended time for brainstorming and open discussion. And we really hope that these sessions and discussions will help us identify connections across different approaches, highlight open questions, and inspire new collaborations. To help the workshop run smoothly, we ask that speakers please be ready with their presentation before their session begins, and please be respectful of time. Please do not interrupt speakers during their talks. You can drop any comments or questions in the chat. It will be moderated by the LOC. For invited talks, they're about 15 minutes in length, and we will allow about 3 minutes of Q&A during the transition period. For lightning talks, which are about 5 minutes because of their short length, please hold your questions until the discussion session. And remember, the discussion session is the best time to raise any remaining questions, expand on ideas, and brainstorm openly. We ask that everyone keep the discussions constructive. Questions are highly encouraged, but please focus on building understanding and advancing science rather than dismissing or negating someone else's results. Also, just wanted to highlight there has been a schedule change. So this is the new schedule right now. The schedule has been updated on the website, so you could follow along there. And I included the link in the chat. So, oops. Okay, so with these guidelines in place, we look forward to a stimulating day of science, and we hope that these talks and discussions will help deepen our understanding of inertial modes. So thank you for joining us today, and we can get started with our first talk.
All right. So this is Junwei Zhao from Stanford University. I'm going to chair the first session. The first session today is what the inertial modes can tell us about solar activity. We are very pleased to have the first invited speaker, Laurent Gizon, from Max Planck Institute of Germany. Okay, so Laurent, it's your stage. Okay, thank you very much, Laurent. So now we have to move on to the next speaker. Next, we have another invited speech by Teimuraz Zaqarashvili from University of Graz, as well as Ilia State University. His presentation is on Rossby waves and solar activity variations. Now, Teimuraz, the stage is yours.
Okay, thank you very much for this nice workshop. So I was asked to make some presentation about Rossby waves and the solar activity. So first I will do some short introduction, and then some old results, and finally I will present some new results about connection of Rossby waves with solar activity. So you all know that the large-scale structure and motions in the Earth's atmosphere and oceans are governed by Rossby waves, and these waves are produced by Coriolis force because of conservation of absolute vorticity, which is the sum of planetary and relative vorticity. So you see this conservation. So then, because of Earth's Earth's vorticity is changing from polar to equatorial region, then when the fluid moves from along the latitude, then of course the relative vorticity should be also changed in order to keep the full vorticity constant. That's the cause of Rossby waves. So this is a nice example, the left-hand side. So you have initially you have vortices, and then you take a particular position, and then you put in time. So you see the nice motion of these vortices in the left-hand side, to the left-hand side. This is famous formula diagram. And then the very important thing is that these waves, which I call Rossby waves, which is more, I mean, for me, it's more convenient. So the dispersion relations you see here in the rectangular case, kx and ky are the wave numbers in x and y direction, and beta is the beta parameter is related with the Coriolis force. This is for the spherical case. So now the why these waves are go to the retrograde direction. Most simple explanation is this following. So if we have no variation of Coriolis force, then at each latitude we will see some motion of plasma in the cycle, right? So this cycle is increasing when you go to the equatorial region. So now if actually the Coriolis force depends on the latitude, then when medium is moving, when fluid is moving to equatorial direction, then the radius is increasing, and then when it goes up, then again decreasing. So you have quite nice retrograde drift. And so I will not touch too much about observation. Laurent already did so. So there are the first observations of Rossby waves are here, with this in bright points, and then with Laurent at the coast there are many different papers, but I just presented the first one, so I will not continue. So Laurent already did some introduction. Now the interesting point is what happens if we include the magnetic field in this description. So then when we have, for example, the toroidal magnetic field, then usual hydrodynamic Rossby waves, which is this red dashed line, is split into two. Yeah, like sound waves is split into fast and slow MHD waves. And then here you have also two waves, so fast and the slow MHD waves. So the magnetic field actually splits the modes, and one mode propagates still in a retrograde direction. This is a fast mode, and another drifts to the prograde direction. This is a slow waves. Also the frequency of the waves are different. Fast mode frequency is higher, and the low mode frequency is lower. So now if we look to this famous diagram, we see that actually besides the Schwabe cycle, 11-year oscillation, we also have some variation in the shorter period and also in the longer, but let's concentrate on the shorter one. So you see that this activity varies in a shorter period than solar cycle. And actually when you make analysis of different activity indices like sunspot area, so photospheric flux, then you see that there are actually very nice indication of variation of the activity in some kind of 150-70 days, so-called Rieger type periodicity. You see this in sunspot area and also in flux. But there are many other activity indices which shows actually this variation. And then there are also some quasi-biennial oscillations seen in differential rotation, and also some radio flux, etc. So in principle, we have indication that the solar activity also varies in shorter time scales. So now, how the Rossby waves can be related with this activity variations? So we more or less, well, some people suggest that there is the tachocline below the convection zone. Some people say that it does not, but I think it's quite logical to consider this layer, which is located below the convection zone. And the width of this tachocline is 10 to 20 megameters, could be 30, then no one knows exact thickness. And then we know that the dynamo-magnetic field is amplified in this tachocline. Then if we have some variation of Rossby timescales in the tachocline, then the erupted magnetic flux, when you have the modulation of magnetic field, may also show the same periodic variation at the surface when it's erupted to the surface in sunspots, etc. So now the idea is what happens in this layer if we consider Rossby waves there. So then, because of the shallow layer of this, it's a very logical to consider shallow water approximation. And with magnetic field, it was done almost 25 years ago by Peter in MHD shallow water equations. And just remind that the layer thickness is should be less than density scale height. So the density is constant, medium is incompressible, and the vertical velocity and magnetic field are independent of vertical coordinate. And vertical velocity and magnetic field are linear functions of vertical coordinate. So the important parameter which governs the dynamics of this shallow layer is this parameter. So the main point is that if this parameter is small, so the reduced gravity is big, or we have fast rotation, then we have the waves which are excited in this layer are trapped near the equator. But in a different case, you have when epsilon is different. I mean, when epsilon is much bigger, yeah, then it's near the equator. If epsilon is very small, then you can consider easily to the Rossby waves. Now in 2010 we made the analysis of differential rotation and toroidal magnetic field, and we found the modes which are unstable. It's very similar what Laurent just said. It's a high latitude mode, m equals 1. We also found exactly the same results, that with m equals 1 modes are unstable. Yeah? So you see here that for different toroidal magnetic field strengths, you have one mode which is excited with a higher growth rate. So MCEI is the growth rate, and here MCA is the frequency or phase speed. So now see that when point 18 is 150 days. So actually these unstable modes have very similar time scale as for observed Rieger periods at the surface. So we thought that this is related, that the periodicity which is observed near the surface is related with unstable Rossby waves below the convection zone. So now another important physical processes play between differential rotation and Rossby waves, because both are a vorticity actually, because differential rotation is a vorticity. And then we have the energy exchange, similar what just Laurent said, energy exchange between differential rotation and Rossby waves. And the time scale, which is time scale of this energy exchange, could be 1 year or something like this. So one could take seriously into account this. It needs more work in this direction. And if we have some, we know that this observed periodicity are due to Rossby waves which are excited in the tachocline, then one can use the observed periods and also tachocline theory of Rossby waves and to extract the magnetic field strength, because the dispersion relation of fast and slow MHD Rossby waves depends on magnetic field. So other parameters are more or less known, density and rotation, etc. So now if we use this and then compare this with the observations, then we can find that actually the Rieger periodicity is anticorrelated with solar cycle strengths. So you see here this wavelet diagram for several solar cycles. And then it seems that when the cycle is stronger, the Rieger periodicity is smaller, with smaller period. So now if we, so you see here how solar cycle strengths and the period is related for different solar cycles. So now we can estimate the magnetic field with this observation and theory, and we can find what you see here, that in stronger cycle, the magnetic field, toroidal magnetic field in the tachocline is around 40 kilogauss, while in the weaker cycles, it's around 20 kilogauss. It's quite close to the suggested values in the tachocline. So now we say that when epsilon is very big, then the waves are concentrated near the equator. So you see here one of my paper 2018. So then the very important point is that the period of Rossby waves in this particular case, when reduced gravity is small, goes very long period, and the fast magneto-Rossby waves goes almost near the solar cycle period, and the slow magneto-Rossby waves even have even a longer period. Now the question is if these Rossby waves are related with some solar cycles. However, the main weakness of this theory is that the magnetic field does not change with. So you cannot generate actually the poloidal field from the toroidal. This is my main point of dynamo theory. Then the idea was, recent idea was to include the dynamo action in the MHD shallow water equations. So we did it in the recent work, which is already accepted in astronomy, astrophysics. So we wrote the MHD shallow water equations with the alpha effect. There is one additional term in the equations because actually when we have the convection, we have the penetration of convection in the tachocline. So in the upper tachocline, where the convection penetrates, one can consider this additional alpha term in the equations. And so then, and we obtained very interesting results. So this is a very simple analytical calculation. We only consider linear waves in beta plane approximation. So we found the very interesting points here. So we have actually two waves, different types of waves, one Rossby waves and dynamo waves because of alpha, which is a dynamo coefficient. Now these two waves are coupled, and it depends on different parameters. So now for if this alpha is big enough, which is obtained by mixing length theory, for example, like this, then one can see that the modified dynamo waves have the periods very close to the Rieger type period, around 150 days or something like this, or 170. And the modified fast magneto-Rossby waves have a period of years, and they are very close to the solar cycle timescales, and even longer if you go to a strong magnetic field. So now this is the case when you have relatively big alpha and reduced gravity, smaller reduced gravity. Now, one can also obtain these two different time scales which are observed in the solar activity. So in this case, we get that 40-45 kilogauss is in this toroidal field, you can get two different time scales. So now
you have 1 more minute.
Yeah. I'm just finishing. So now, if we now take the alpha is smaller, because in this case, in the dynamo theory, you are getting the solar scale time scales, and reduced gravity is increased. Then we get also two different modes: modified fast magneto Rossby waves, which has the period around the Rieger type periodicity, and modified dynamo waves, which has two different components. Yeah? One is close to the solar cycle, Schwabe cycle timescale, and another is 100 years, which is also observed in solar cycle variations. So in principle, this is only just the first step, only simple linear case, but more more analysis also with numerical simulations are in the way. My PhD student is now looking to this case in more detail with numerical simulation. So probably soon we will have more more results in this direction. So this kind of situation, these three different time scales actually which are observed can be realized in 14-15 kilogauss below the convection zone. So this is all. This is just a conclusion. So thank you very much for your attention.
Thank you for the nice presentation. Now we have time for 1 or 2 questions. Okay. Yeah, Gustavo.
Okay.
Yeah, hi. If nobody asks, I have questions. Thank you so much. So it seems that this fast magnetic wave, it has a very long period. So perhaps we don't observe these modes because we have not sufficient observations.
You mean period of 150 days or even
No,
longer?
25 longer. Yeah, the longer one.
Well, what I said is that actually, if we have the time scales in the Tahoe line, then it will probably will also influence the cyclic variation what we see. So this long-term variation, like 100 years, Gleisberg cycle is actually observed.
Okay.
Yeah.
And another question. So you have two dispersion relations when you include the magnetic field, right? And the dispersion relation for the retrograde modes is a little bit different from the hydrodynamic one.
Yes.
Yeah, this one.
Yeah.
But when we observe, we get the hydro one. Do you have any idea why we are not getting the dispersion relation for with magnetic field? Perhaps the solar magnetic field is so weak?
Yes, that's a very good question, actually. Yes, this is true that we observe only hydrodynamic Rossby waves in the surface. Yeah, as Laurent and others, they usually only it's quite possible that there is also the slow MHD waves which propagate in a prograde direction. It depends what you take. For example, if you take the Carrington rotation as a frame, then you may get, and if you take equator, for example, you may get different prograde. Also, you get the prograde waves. So I don't know. It's observations should tell us maybe there are also fast and slow modes in the surface. But in the Tahoe line, it's very hard, of course, to observe because we only see what they influence at the surface. Yeah? We don't directly see them in the Tahoe line. If helioseismology will tell us something, that would be a great.
Thank you.
Okay, I have a very short question. So besides the periodicity, so what else do we look for on surface for the existence of magneto-Rossby waves?
You mean
have any
in the surface or in the Tahoe line?
On surface? If we want to look for for more evidence.
Yes, in surface, what people, Laurent and others, they also observe the wavelengths. I mean, they have the both frequency and wavelengths. So one can make the analysis in space and time. So you get everything what they have. I mean, they are giving us frequency and wavelengths as well.
All right, thank you very much. Now let's move on to our lightning sessions. Today we have, for this session, we have 3 lightning talks. The first one is by Gustavo Guerrero from UFMG of Brazil. And his talk is on simulation of onset and nonlinear evolution of solar and stellar inertial waves. So Gustavo, you can start.
Hi, can you hear me?
Yes.
Okay, thank you. So very short talk. So let me just start from here. This is a paper that we are submitting this week to APA. The name is Nonlinear Simulations of the Onset and Nonlinear Dynamics of Inertial Waves in Solar and Stellar Interiors. This is the work of my former master student, Marianne Sousa, also completed by Conrado Finotti, who will speak later than me, and other collaborators, including Mausumi Dikpati, which is in the audience, So we were looking for a 3D model that was able to capture all these dynamics, and then we use the Euler code. This is an inelastic code that solves this equation. So we force the velocity to get the solar differential rotation. We force this profile of differential rotation. And then we allow for perturbations in velocity, of course, and we also allow for perturbations in the potential temperature, which is related with the entropy, right? And then we can, this parameter here tell us about the thermal stratification, about the interior of our model, and we chose this very close to the solar standard model of Georgi Christensen Dalsgaard. So when we allow all these perturbations to evolve freely or with some time scale, what we obtain is this. Very quickly, we develop mean flows, and these mean flows are the differential rotation, of course, but we also develop non-axisymmetric modes. And this depends in the amount of shear that we impose in the simulation. So if the simulation doesn't have sufficient shear, then we don't have instability, and the growth rate of these modes increase progressively until our simulation with 40% of shear, relative shear between equator and pole. And here we obtain that the first instability, and here we have a secondary instability, which may or not be what Laurent just mentioned as a bifurcation. So these are the profiles of differential rotation that is obtained with the simulation. Of course, this is forced, but together with this differential rotation, the simulation automatically it obeys thermal wind balance. So it develops meridional circulation and it develops a gradient of entropy. Here is a gradient of potential temperature. Okay, so the simulation is in perfect thermal wind balance when it's saturated. And here are 3 different values for 3 different values of shear, and I will start playing these movies, which will show how these simulations go. So to begin with, the instability starts at higher latitudes, at the pole. When the shear is small, then the instability grows slowly, but when the shear is high, the instability grows very, very fast. And here, the 20% shear, which is a value closer to the sun, we obtain this polar vortex, similar to the one that is observed. But when we go to 40% shear, Then we have this instability at the poles. We have the polar vortex, but we have a strong inertial modes at the equator. And in between, a simulation that is not presented here, but it's in the paper, with 35% shear, we have a mix between this case and this case. So perhaps this is the bifurcation that Laurent was talking about. So we compute the spectra of these simulations, and we obtain results that are very close to the observations. This is the case for 20% shear, and this is the yellow line here is the dispersion relation for the high latitude modes, and this yellow line is for the equatorial mode. So you see that we don't get excitation of equatorial modes with 20% shear. So in this case, we impose a perturbation in the system, and this perturbation has a single mode, n equal L equal 10, and immediately this perturbation propagates along all the available modes following the Rossby waves dispersion relation. So any perturbation that we impose on the system just propagates along the Rossby waves dispersion relation. This is quite important because we demonstrate that there is an inverse and direct cascade propagating the energy of these modes. And also we get transport of angular momentum. The stronger the shear, the larger the transport of angular momentum. So this red is transport of angular momentum. The negative value here in the northern hemisphere implies that these inertial waves developed at the high latitudes are accelerating the poles. And when the shear is very strong, then we have a very high acceleration of the poles. So my conclusions: the origin of the high latitude modes is the baroclinic instability. We demonstrate this by comparing the growth rate with the thermal wind balance component. This mechanism does not excite equatorial Rossby waves. However, any single mode perturbation cascades to all available scales along the Rossby waves dispersion relation. The angular momentum transport due to these high latitude modes tend to accelerate the poles. Yeah, so if you have questions, please let me know in the discussion session. Thank you.
Thank you very much. So we don't have time for questions for lightning talks. We will have questions in the discussion sessions. So our next speaker is Conrado Finotti, also from UFMG of Brazil, and his talk is on influence of magnetic field on solar inertial modes. Okay, you can start.
Thank you very much. Hello everyone. My name is Conrado Finotti. I'm a master's student at Universidade Federal de Minas Gerais, Brazil, and I will talk about my work on the influence of magnetic field on solar inertial modes under the supervision of Gustavo Guerrero. So following Gustavo's talk, let me briefly highlight how we extend this to MHD. The same equations are solved, but now we add magnetic field. So we have the Lorentz force in the momentum equation and also a new induction equation. So we impose an initial poloidal field. After the hydrodynamical simulation, we restart the simulation, which is initialized as 10 Gauss, which is the solar minimum value for the poloidal magnetic field. And then here you can see the animation of the turbulent velocity of the longitudinal component in the top and the bottom right animations. In the bottom left, you can see the magnetic field lines evolution. As you can see, the poloidal magnetic field rapidly evolves into toroidal field lines because of the omega effect. And you can see that the magnetic field strength is strongest at places which the shear is greatest, which are in the tachocline and surface at mid to high latitudes. Also, you can see in the turbulent velocity animations that the morphology of the polar vortex is changed, and you can see the excitation and propagation of inertial modes in different depths and latitudes. So here we quickly compare the spectra between the HD case, which is the left panel, and the MHD case, which is the right panel. You can see very clearly that in the MHD case, there's propagation below the tachocline, when in the case of no magnetic field, you can see this feature. Also, you can see the prominent feature of equatorial Rossby modes in all radii are plotted here, which is a new result. Observations found by Boyang Ding in 2025 states that the M equals 1 high latitude mode power near the surface and have an anti-correlation with the zonal flow and sunspot number. So you can see the time window of interest that we are going to compare in this left picture. You can see for our results, they match pretty well with the observations, because you can see the here we have the solar minimum, and then we have the solar maximum. So in this time window of interest and at near surface layer, the results of observations and our model match pretty well. But it's a bit more complicated at the tachocline. As you can see here, the anti-correlation becomes a strong positive correlation between mode power and magnetic field and zonal flow. So the conclusions of our work is that the magnetic field plays a significant role in the evolution of the inertial modes and also modifies the spatial scale of the high latitude modes and excites the equatorial Rossby modes as well. Conversely, the high latitude modes influence the magnetic field at polar latitudes, and this might enhance the turbulent diffusivity at those latitudes. As you can see, as you saw in the animation, the magnetic field lines wobbles at the polar regions. At surface levels, the time evolution of the M equals 1 and M equals 0, which is the zonal flow, anti-correlates and correlates with the magnetic field strength, respectively, such as the observations point out. And however, the correlations change with depth, as you can see in the bottom left figure. Yeah. Thank you very much for your time, and I'm open to questions.
Thank you. Okay, so we move on to the next lightning talk. Next one is by Mausumi Dikpati, and her presentation is on Rossby waves in shaping longitude distribution of solar activity. Mausumi, you can start.
Okay, somehow I can't make my video on. Okay, start video. Yeah. So I'll be talking about
Do you want to make it a full screen? Make it a full screen.
Right. Slides. So what happened?
Oh, you stopped sharing.
Okay.
Okay. Now it's good.
Well, I am not presenting any solid new work. I'm just reviewing some of the things. So how Rossby waves play a role in shaping the longitude distribution of solar activity. The bipolar active regions that emerge at the surface, generally one of the most plausible explanation is that the axisymmetric toroidal magnetic field from the bottom of the convection zone or from the tachocline region emerged to the surface through undular instability. Now, if you think of only one of them, active region, then you can think of this theory. However, when you look at the magnetogram observations, you see that many of those at the same time at different longitudes, different latitude, longitude, latitude distribution is not so big at a time. Longitude, there are several longitudes, and they follow a pattern, and this is a warp toroid pattern, and you can see this is purely from observation, and you can see that they are basically the combination of like m equal to 1 to 3 modes, probably dominated by m equal to 2 modes in this case, and it is m equal to 2 dominantly antisymmetric about the equator, but there are other modes combined, so you cannot say a one particular symmetry prevailing throughout. So, and they evolve. These are 3 Carrington rotations. This case is from Halloween storm case. So 2007 Carrington rotation, 2008, 2009. So you can see the pattern is evolving, but that there is a pattern which comes from the combination of different modes. So basically, what creates this pattern? This is most likely not occurring in the bulk of the convection zone. It is probably occurring from the region where it is more subdiabatically stratified, so organized pattern can be possible. And Rossby waves interacting with dynamo-generated magnetic field, axisymmetric magnetic toroidal band can be a one of the plausible candidate to create this kind of pattern. So here you see the evolution and you see the pattern, and sometimes it's more dominated by m equal to 2 modes, sometimes combination of m equal to 1 to 3 modes. I mean, it can be higher modes also to some extent. Here is a movie I am showing. So basically that longitude pattern, organized longitude pattern is most likely being generated from a layer more subdiabatically stratified, and due to the nonlinear interaction between magnetic field differential rotation and Rossby waves. So I didn't want to spend too much time on this, and if you have question right now, I can answer, but we can also discuss during the discussion session. Thank you.
Okay, thank you very much, Mausumi. Now we conclude our presentation part of the session. We will start the discussion part of the session. We will have about 25 minutes for free discussions. I think so. All the audience can feel free to ask questions to any of our previous speakers. And also, I mean, all the audience can have free discussions as long as you have burning questions to discuss. All right. So we have Antique Barrick raising hands. Yeah, go ahead.
Hi, so I had a question for Gustavo. So you mentioned that in some of your simulations, you see a polar vortex and an equatorial inertial mode. I think at least in one of those cases, to me, it seems like it's more of a single mode that has gotten twisted by the differential rotation rather than 2 distinct phenomena. And that is something we also saw in my old work with Santiago that we did with radial differential rotation, that we saw tangent cylinder effect where the mode got twisted because of the differential rotation, but it was still the same mode.
Yes, I agree. This may be. because if we see the modes, we plot the modes in the frame rotate at the equator, let's say, which has the same rotation than the frame. We see exactly the same dispersion relation of the same modes that we see at the poles. So it's exactly what you are saying.
So I saw in the chat, Amy Norton had a question to Gustavo. So Amy, do you want to repeat the question so that everybody?
Yeah. So I was trying to connect some of these modes with what we see in the eruption of the sunspots. And you often see an increase in a higher M mode in the sunspots. So you might see an M = 4, M = 6 at certain times in the solar cycle. And I saw in the 10% shear case that Gustavo showed, there was an antisymmetric across the equator higher M mode. And so I asked him about it and if he thought they could connect. And I don't quite understand why you say not sure if they connect with the observations.
Yeah, because the shear is too small to be the sun. It's only 10% shear between equator and pole. And the case that relates mostly with the sun is the one with 20%. I believe the precise value for the sun is 18%. And in that case, with 20% shear, we don't observe equatorial modes very strong in the hydro case. But if you see the movies that Conrado presented, the magnetic field excites these modes. So it's a combination of the modes that are already there enhanced by the magnetic field. And these might be the modes that you are observing. Of course, we only have one part of the cycle. We go from the minimum, where the magnetic field is just poloidal, to the maximum, where the magnetic field is mostly toroidal. But in our simulation, we don't have any alpha effect. So we don't know what is further. But until there, we can examine the modes and try to compare with your observations.
Okay, thank you.
I also have a short question to Gustavo. Can you bring back your presentation? Also, I think Conrado also showed similar plot on the power spectrum. I just want to clarify. Yeah, this page. I just want to clarify here. You see this branch of power spectrum. So do you know any observational evidence of this branch, and what exactly is it? Can you clarify again? I'm not sure if I understood it.
Sorry, which branch, Yungwei?
Oh, you can. I plotted it on the screen. Did you see?
Oh, I didn't see. Can you point it again?
Oh, okay.
Because my screen became a screen with a lot of little faces. So maybe you can tell me what what radius and what latitude.
So I make this one, just the negative slope with you cannot see. Can you see my drawing? No.
No, it's because I am with the presentation.
It's on the middle panel.
So
middle
panel. Middle panel.
Ah, it's the central one. Yes.
So radius 0.66 and middle latitudes.
Middle latitude. Yeah, it's the negative slope, the dashed line.
Right. So that's the same polar modes. And now the tilt is different because for every one of these panels, we are correcting for Doppler deviation. So the modes are the same.
Okay.
The this is complicated to make this, and we did it in a very simplified way by taking average of the rotation every panel, and then we corrected to Doppler shift. But then, so you see the tilt is different of the yellow line, but they are exactly the same modes. They obey the same dispersion relation.
Okay, thank you. So next one, I saw Lucas raising hand. So Lucas.
I have a question following up to Laurent, if he's already here, if it's still here.
Still here.
I would like to ask, yeah, so how do you get this meridional entropy profile from the observation? What are the hypotheses for this?
Just the thermal wind balance. That's how we compute it. Yeah, the entropy gradient.
Okay, so there's no other flow component.
There's no.
So
we specify the rotation profile and deduce this. I think this should be pretty good throughout most of the convection zone. Very near the surface, I guess it's not quite right, but yeah.
So there's like no Reynolds stress, no whatsoever.
To compute the entropy gradient, no.
Okay, thank you.
Yeah.
So next one we have Ankit.
My question is for Gustavo again. So Pascal Guerrero back in 2001 had a paper on looking at the instability of just the differential rotation itself. And she found that through shear instabilities, you can get these large-scale Rossby modes and so on. Have you compared your work with hers? Does it reconcile?
Not really. If I'm not mistaken, this work was for latitudinal differential rotation, isn't it?
Right. Right.
And if I can share my screen again, what is really important here is the radial differential rotation. I can show you some backup figure that I have here. Oh, I'm sharing. Good. So if you see this figure here, we have the growth rate, and it agrees.
I don't see your screen currently.
Okay. Yeah. What about now?
Yeah.
Okay. So this figure, you see the black line is the growth rate computed from the results, okay?
Mm-hmm.
And then we compare this growth rate with the radial shear at the poles, the radial shear and taco climb,
right?
And also with the latitudinal shear of potential temperature at the taco climb too. And then you see that there is a very good correlation between the three. This makes us, or this confirms that the instability that we are seeing is the baroclinic instability, and it happens because of the radial shear. The latitudinal shear may be contributing, but is marginal. What is more important is this.
Okay, thank you. One more, just a comment I had was when you mentioned that when you have the magnetic field, sometimes it actually contributes to the mode and contributes to energizing the mode more. That's something I have also observed in sort of very simplified models where I excite with radial shear. When you apply a magnetic field, sometimes the growth rate suddenly jumps up quite a bit. So it's very interesting to see.
Yeah, then maybe Conrado can say something. I don't think he has computed the growth rates yet, but we can compare the growth rates of the hydro and the magnetic case.
Yeah. That would be interesting to see if you have a larger growth rate from the magnetic field.
Yeah, we didn't compute the growth rates, but talking about like the mode power, as I showed in the last slide of my presentation, you can see that at higher latitudes, you can see an anti-correlation between magnetic field and the m = 1 mode. So like the magnetic field kind of slows down the background M equals one mode, but
Right.
the behavior is much more complex when we analyze different modes, like different M equals 2 high latitude mode and also different depth and latitude. So yeah, in general, it enhances the inertial modes in general, but it's more nuanced than this. Yeah.
I think it might also have to do with the symmetry properties of the field versus the mode as well. If
Yeah,
they're
sure.
compatible or not. Yeah.
Yeah, of course. And also in the animations I showed, especially in the magnetic field line evolution animation, you can see that the toroidal, the strongest toroidal fields are usually trapped in areas where the mode is strongest. So yeah, and it's a big correlation, I feel like.
Okay. I do have more questions, but I'll let Mausumi go first.
On the same, oh, sorry.
Yeah, Laurent, you want to say? Go ahead.
Yeah, on the exact same topic, I showed in my presentation a kernel for the linear growth rate for the toroidal field. And we find that the growth rate goes down with the field.
Okay. And
yeah.
when you use toroidal field, what kind is it, like a Malkus field, simple?
Simple
B5.
B5. Yeah, that's right.
Okay. And does it change with radius in any way, or it's a constant B5?
It changes, yes, a little bit. There's yeah.
Okay.
Ankit, if your question is related to this, you can continue asking.
Yeah, that was my question. Is it like it's a B5 that sort of linearly varies with radius, or what is the exact geometry of the field? Is my question in both your cases, Conrado.
What we did,
and
what we did is simply to take a flux tube, so B5 radius was around 0.08 solar radius, or diameter maybe, and we move it at different, locations in the convection zone, and so we can see how the growth rate changes with position.
Oh, I see.
Can I make some comment?
Oh, sure. Yes, go ahead.
Yeah, actually, we also may have the same result in 2010 instability of Rossby waves with different magnetic field. And we also found that the growth rate is reduced for stronger field. So you could see in my plot what I presented in my talk.
But I suspect it's also dependent on the mode itself.
Yeah. So we also did only linear instability. I mean,
yes,
but we
of course.
took not a simple profile, but the profile, antisymmetric profile of magnetic field with the latitude.
May I make a comment also in this direction? Actually, it depends on the mode. If you are thinking of only m equal to one mode, then it increases first with magnetic field, and then it reaches asymptotic. It doesn't decrease. There is a no cutoff. But if you think of m greater than one mode, m equal to 2, 3, 4, then it has a cutoff. So it first increases a little bit, then it decreases with magnetic field and has a cutoff. Linear growth rate.
So okay, so Mausumi, you still have
Yes,
your hand raised. Yeah.
I have two questions, one for Laurent and one for Teimuraz. So first observational question I'm asking, how consistent are Rossby waves detected from different instruments like HMI, GONG, solar orbiter? And what do they say about robustness? To Laurent.
Okay. Yeah, thanks for the question. That's an important one. I think I should really leave this to Jichao, who will actually compare the results from at least 3 different independent data sets. But overall, there's excellent consistency. Maybe the early days of Mount Wilson data is a bit more noisy. I mean, that's understandable, but otherwise there's a very good consistency. Especially Gong and HMI, I think it's very good. Yeah. Maybe
so Jichao, do you want to say more about this?
You will show this right later. Yeah. He's here. He's here.
He is here. What? You are still in office?
Yeah. Later in my slides, there's a comparison between different data sets, the curves on data sets.
All right.
Maybe I asked the question a little earlier, so I should have asked that after listening to his talk. So the question for Teimuraz is similar, but on the theoretical side. How robust are the theoretical models in distinguishing between the hydrodynamic Rossby waves, magnetized Rossby waves, and Alfvén waves in the solar interior or wherever they are getting generated?
Yeah, this is a interesting question. So I mean, hydrodynamic Rossby waves is very simple. I mean, we understand it nicely, but when you include the magnetic field, well, we can also understand your paper also. It's interesting about physics of MHD Rossby waves. But when you include this new dynamo term and consider these Rossby dynamo waves, many things are not quite clear in this case. Because I expect that we will get changing of sign of magnetic field, which is very important for dynamo, and also the equatorial drift of the sunspots. But how robust? Well, it's difficult to say, because you need more numerical simulations, more to go deep into the field, because it's a new direction. So we need much more. What we see only just periods, what we got from the linear analysis, right? But well, we will see in future. I hope we will get nice results. All of us, I know.
Thank you.
Okay, so no more questions. So if there's no more question, I will copy and paste the one question to everybody, including all the speakers and audience. I will post it in the chat, and so that we can have a discussion. Okay. So how will inertial modes help us to understand the solar interior dynamics, such as rotation, meridional circulation, viscosity, heat conduction, and others? So I believe a few speakers already touched this question, but I want to hopefully everybody can express their opinions on this topic again. So maybe Laurent, I think you have a lot of experiences in doing this. Do you want to say something about this question?
So I definitely do not have any definitive answers. It's a lot of questions, by the way. What's the one thing that I think is pretty safe to say is that these modes are indeed sensitive to some of these quantities that you mentioned. And when I say they're sensitive, it means that the observations together with the error bars that go with them are susceptible of being able to constrain models. Yeah. So we are pretty sure that things like the superadiabatic temperature gradient, for example, can be constrained. And we hope that we can extract some kind of a radial profile for this quantity if we combine all the modes. Yeah. For the viscosity also, we should be able to, turbulent viscosity, we should be able to do a good job. For the rotation, I showed you an example. It should work. We will not learn that much, of course, because we have a very good P-mode answer already. Then the magnetic field, you heard everybody. I mean, I think there are lots of hopes here to really get something really new. So that's very exciting. But in order to get to the magnetic field, I think there are a few things that have to be done. So I gave the example, for example, of the effect of the torsional oscillation on the modes. It's a significant component, and it has to be properly computed in order to look at the remaining residuals. Yeah, so there's I think lots of hopes. Now what we realize also is that in order to, because we're talking about tens of nanohertz, so it's very small. I mean, sometimes it's 2-3 nanohertz, sometimes it's even less than that. It's really important to have accurate solvers. Yeah, whether they are linear solvers or nonlinear solvers, they have to be extremely accurate. And that's something we realized ourselves. I showed an example, for example, for the rotation, where we had one student who had an answer and another student another answer. They were off by, I don't know, 3 nanohertz. And we had to work pretty hard to find the reasons for these discrepancies. Yeah. And yeah, it will take some work, I think, to have some really reliable, accurate solvers. Yeah, that's one answer maybe.
Okay, yeah, excellent. Yeah, I thank you very much for sharing your opinion. We look forward to some new results about solar interior.
Can I make some comment?
Sure. Yes, please.
I think the very important thing in MHD consideration is the magnetic field strength in the dynamo layer. So what we tried is to estimate this magnetic field from the observation of periods in activity, but this is not. I mean, this is not robust because you only see period, not the wavelengths at the surface. Because the eruption of magnetic flux goes not in direct, but it make a very large eruption latitude. So I think the seismology may help if it's possible, I don't know, to estimate the magnetic field in this layer. What the Laurent already made some results. So if we go to the below the convection zone with the helioseismology and estimate magnetic field, then it could be very, very important for general physics of this regards. So strength of magnetic field is very important.
Yeah, maybe I can add a small thing also. We saw that it's to complement what Teimuraz was saying. We saw that even in the hydro case, it's important to include at least part of the radiative zone in these calculations. If we stop, exactly at 0.7 solar radius, there is a difference between such models and a model that would, include part of the radiative zone. These are small differences, but they matter. And if you add on top of this a magnetic field, of course, it's even worse in a type of climate.
I do agree. By the way, the subadiabaticity, the radiative zone is completely different from the one in the convection zone. So it has to be taken into account, that value too.
All right, so I'm afraid that I have to conclude this session. It's already 5 minutes past the time. I saw also Ankit have more questions, but I think if possible, we can continue to discuss in the next session's discussion part. Okay, so we will have 10 minutes, 15 minutes. I'm sorry, let me take a look. Yeah. We have 20 minutes of break until 10 a.m. of Pacific time. Okay, 20 minutes from now, we are going to start session 2. Okay, let's take a break. Thank you very much.